energy. You see, the Chinese word for physics is the dance of energy. The whole universe is a great big dance of energy. Energy gets converted from one form to another continuously. In fact, the whole of the universe is actually a big, great big pot of energy. And the universe that we know is simply a small bubble in there, a simple bubble. You see that? A bubble comes, and that is what we are, the whole of the universe. And that bubble can burst and form another bubble. The big universe is simply a great big dance of energy. Energy continuously gets transformed from one form to another. You and I are part of that small bit of energy. And we will eventually get back and become part of that energy. We are all part of that great big soup of energy. Isn't that wonderful? And physics gets very interesting and fascinating when you want to study that great big pot of energy. In fact, in trying to answer the question, what is that everything that we see? What are we made of? What is everything in the universe made of? It takes us to the very core of this question. Everything is made of little strands of energy called strings. In fact, the whole of the universe is a great big haze of that string. And depending on the resonance pattern, it can change different shapes and forms. And universe is a continuously changing, boiling pot of energy. Well, at the moment we have no time to talk about it, so let's now go and discuss the concept of work energy theorem. Work energy theorem is a consequence of the conservation of energy. What is conservation of energy we talked about? Conservation of energy tells us that the net change in energy is always zero. Work energy theorem is a consequence of the law of conservation of energy. Alright, now here I have a slide. A child is sitting on top of that slide, and the slide is at a height h from the ground. The girl on the slide has a potential energy U equal to mgh. If she now slides down, she gains kinetic energy at the expense of potential energy. Now, so at the bottom, actually all that potential energy will become kinetic energy, so that delta U plus delta K equal to 0. The net change in the energy equal to 0, or all the potential energy lost will become kinetic energy. But in actual fact, all the potential energy lost may not become kinetic energy. Well, if all the potential energy gained becomes kinetic energy, this girl will break her jaw by the time she lands, because her speed will be enormous. There is some energy lost in work done against a non-conservative force. You see that? There is friction here, and some energy is used in doing work against that friction. And therefore, it is more convenient to say in this case that there is a net change in energy, and that net change in energy is used in doing work against friction, against the non-conservative force. Well, let's talk about that. But in practice, some energy is used in doing work against the non-conservative frictional force as she slides down. That means we will now be able to amend the equation like this. for all practical purposes, we would say the net change in energy is a measure of the work done against friction. The net change is a measure of the work done against friction. And this statement is what we call the work energy theorem. And it's a very important statement. What does the statement say? The net change in energy is a measure of the work done against non-conservative forces. Well, we will use this concept to solve problems in the next part of the lesson. Before I close this lesson, I would like to show you an application of the conservation of energy principle. Well, you're all familiar with the roller coaster. Now, when you want to ride the big Kumba, is that right, on, where is that? In Tampa, is that right? Now, the car is taken to a great height, is that right? That's when the energy is used. Work is done to drive the car up, and then you let it go. What happens? Well, it really didn't do very well, did it? Well, you can see the potential energy it had become kinetic energy at the bottom. The kinetic energy is converted to potential energy, and it will continue. Let's see one more time. If I leave it here, there you are. So the continuous conversion from potential energy to kinetic to potential, and the system will continue. And that is a great application of the law of conservation of energy. Alright, I'm going to stop this part of the lesson here. I will see you for solving problems using these concepts in the next part of the lesson.